Let's do Unit 5 progress check for your response questions, Part B, number 2. And it says the number of fish in a small bay is modeled by this function f, defined by this. I've written it on the paper already. T is measured in days, and we are dealing with the interval from 0 to 8 days. So that's going to be good to know as we move forward. Using the correct units, interpret the meaning of f prime of 4 equals negative 30 in the context of the problem. Okay, well, obviously we're dealing with a rate of change, and it is the rate of change of the number of fish per days, and we do need to use the correct units in this, so let's just go ahead and write it. We are dealing with time of 4, day 4. So at day 4, the rate of fish is changing at a rate of negative 30 fish per day, and you could say instead of negative 30 fish per day, you could say it's decreasing at 30 fish per day. So that's what I'm going to write. Here goes, part A. At t equals 4 days, the number of fish in the bay is decreasing at a rate of 30 fish per day. Let me warn you about something. Don't put decreasing at a rate of negative 30, because then you've double used your negative. That's like it's going down by a negative. That would mean it's increasing. So don't do that. You can put your negative in the number. You can put your negative implied in the word decreasing, but don't use it twice. Okay, part B is where things get a little bit more interesting. I mean, part A was interesting, but now it's really going to get interesting. Here goes, part B. Based on the model, what model? This right here, this equation that models that. Models that meaning this. I'm just going to ramble for just a second. This is a continuous function, but the number of fish in the bay is not a continuous function. Any given moment, you're going to have a discrete number of fish. Discrete meaning countable. So if you were to look at the graph of this, the real world graph of this, you'd have fish in a bay, and it would be like this, whereas our function instead is a smooth curve. So we can have fractions of fish in our model, but in the real world, it's not necessarily going to be that way. It's definitely not going to be that way. Otherwise, you don't have a full fish, and the fish is not alive if it's not full. So look at that half a fish swimming there. No, not going to be a thing. Anyway, based on the model, what is the absolute minimum number of fish? Okay, minimum number, that means I'm dealing with the derivative. I need the derivative to equal 0 over the time interval from 0 to 8. Justify your answer. So here's where my mind goes in this one. We are looking for a minimum, so again, where the derivative equals 0, or where the derivative doesn't exist, or maybe we have a minimum number of fish on the endpoints of an interval, and that, everything I just said, is the extreme value theorem. As long as the derivative exists, let me rephrase that, as long as we can take a derivative or determine where the derivative does not exist, then we need to check where the derivative equals 0, we need to check where the derivative doesn't exist, and we need to check the endpoints of an interval. What I meant to say was as long as we have a continuous function, which we do. So let's do that. I'm going to go ahead and begin by taking the derivative of our function. So capital F prime, don't use lowercase f. When I take the derivative of this, don't distribute that 10. Just don't complicate your life that way. Please don't. That's just not nice. It's just 10 times whatever the derivative is. It's just a constant. So 3t squared minus 24t plus 45, and we're going to set this equal to 0. Again, we're looking for where the derivative equals 0. This derivative exists everywhere. We're also going to check the endpoints of our interval, and we will do that in just a moment as well. So let's set this equal to 0. Let's go a little further. 30, I'm factoring out a 3 here, by the way, and then t squared minus 8t plus 15. That's equal to 0. 30, t minus 5, t minus 3 in no particular order, equals 0. So t is equal to 5, and t is also equal to 3. And we have the potential for minimums and maximums at 3 days and 5 days. So we're going to test those. Now, normally I would draw a number line, and we'd go from negative infinity to infinity. No, we're not. We're going from 0 to 8. Now, when it says justify your answer, we'll use words, but this is part of our justification. This is a way that we're kind of expressing what we're doing. So 3, 5. Now we're going to plug numbers from each interval into the derivative. Now, here's the derivative again, here's the derivative again. Let's plug it into this one. This is calculator inactive, and it is totally doable because really all I care about is the sign of the derivative to determine increase or decrease. And I don't need to know the exact number, I just need to know the sign. So I'm going to pick a number in each interval. I'll switch to green for fun. This 1, for example. If I plugged a 1 in here, I would have a positive. That 30 is always positive. We're just going to ignore it from now on. So I'd have a negative here and a negative here. Negative times that positive is going to give me a positive. So my derivative is positive on the interval from 0 to 3 days. Okay, so far the function is increasing. We'll plug in a number from here, like a 4. There's an obvious answer there, obvious guess. Plug in a 4 here, you'd get a negative. Plug in a 4 here, you'd get a positive, and therefore the derivative is negative here. Plug in a 6. Plug in a 6 here and here, we'd have positives. So here goes. Let's interpret what just happened. Again, we're looking for minimums. Minimums occur where the derivative equals 0, so we have a potential for a minimum at 3 and 5. We also have the potential for a minimum at the endpoints of an interval, but let's rule out some of them, okay? My function increases, then decreases, and because of that, 3 is a maximum, so the 3 is a number, a point, that I'm not even going to test. I'm not even going to plug 3 into my function to find out how many fish there were because I know it's not a minimum. So this one is a relative max. And now we'll go to the 5. Now my function was decreasing then increasing. If my function was decreasing then increasing, that is a minimum. So we have a relative minimum here. We will check the 5 and we'll see what happens at 5. Let's look at the 8. As we go from 5 to 8, the function increases some more. So we have a relative max here. We'll start abbreviating. Relative max here on the interval from 0 to 8. And also, let's consider 0. So let's figure out what happens here. As I begin at 0, at day 0, the number of fish in the bay increases. So if the number of fish in the bay was increasing from 0 to 3, then 0 must have been a minimum. Maybe not the minimum, but it was a minimum. We'll call it a relative minimum. Relative minimum. So we are going to check these two t values to find out how many fish there were, and that will tell us, by comparing them, what was the least number of fish. That's what they're asking. So that will be our justification. We will put that into words in just a moment. So let's start by plugging some things in. We're going to plug in 0, we're going to plug in 5, and we can do this without a calculator. It is very much doable without a calculator. So f of 0 is equal to 10 times, okay, let's just not write everything you want to write here. Please don't. There's only so many hours in the day for this. If you plug the 0 here, here, and here, you'd be left with just a 100. So 10 times 100. Whoops, I went ahead and I put the answer in the wrong place. And I have a squeaky chair. Sorry about that. 10 times 100 obviously is going to give me 1,000 fish. Okay. We're going to plug in a 5. This one takes a little bit more work. 10 times 5 cubed, minus 12 times 5 squared, plus 45 times 5, all without a calculator. I think we'll make it. We can do this. So we have 10 times 125. Let's see, that's 25 times 12. 25 times 12 is 300, so minus 300. 45 times 5 is 225, and then we have a 100 here. Here's what I do. This is just me. I like to put ones together that are logical, and it just simplifies my computation. So 10 times, let's see, those two go pretty well together. That's negative 200. Those two go pretty well together. This is just me thinking. I mean, they're all like terms, but I'm just trying to group things logically, just in my head, you know. You don't have to do it this way. 350 from the first and the third term, negative 200 from the last term. And that's going to give me 10 times 150, which is 1,500 fish. Okay, now we have found the minimum number of fish, but we really need to talk about this because they did say justify your answer. Let's make sure that we're actually answering the full question. And the full question is, based on the model, what's the absolute minimum number of fish? Okay. and justify your answer. So let's start justifying things a little bit here. There would be several points awarded on this problem based on the things that you've done. Let me go ahead and just kind of pause here and say this. You would get a point on this one. You get a point for the derivative. You would get a point for setting the derivative equal to 0. So there's 2 points right here, lucky you. Identifying this one as a candidate, and then an answer with a justification. You get 4 points just for part B. On each multiple choice question, you have the potential for 9 points. So part B is the big one on this one. So let's justify a few things here. We have done a lot of work. Let's write some stuff down. So because f prime of t changes, by the way, here's what I'm about to write. I'm just giving you a heads up of where this is going. I'm going to explain to the person who's grading my paper why I used 5 and I didn't use 3. Okay, and you might say, well, what about the 0 and the 8? Okay, we'll talk about that in a minute. Because f prime of t changes from negative, feel free to abbreviate, to positive at t equals 5, then we will consider t equals 5 to be the location of the absolute minimum. No, it's not. Okay, we, according to the way that this one is graded, we did not have to justify why we picked 0, but that is technically according to the extreme value theorem, which again means I choose the endpoints of the interval, and I also choose where the derivative equals 0. But again, don't waste your time with this one and this one. Those are maximums. Here are your minimums. All right, just saying. So final answer is f of 0 equals 1,000 fish. Okay, that takes us to the end of part B. Let us move on to part C. And I want to read this one very, very carefully with you. So here goes. For what values of t from 0 to 8 is the rate of change of the number of fish in the bay decreasing? Whoa, that's kind of wordy. I know. It is. So let's read it very carefully one more time and we'll make sure we're understanding it correctly. For what values of t? Final answer for part C is going to give me a t value, or more than one t value. It might even be an interval, from 0 to 8, is the rate of change, okay, dealing with the derivative, decreasing. Whoa now, actually we're not dealing with the derivative. I want the rate to decrease. I'm dealing with the rate of a rate. I need the second derivative. Okay, so if the rate is decreasing, then the second derivative is negative, okay? So let me read it again and say that. The derivative, the rate of change of the number of fish, is going down. So I need the derivative of the derivative to be negative. So let's find the derivative of the derivative. You know what that is? That's the second derivative. So here's part C. And I'm going to go back to the factored form of the derivative. Don't rewrite it. I'm just doing it because it wasn't immediately on my paper. This would be a waste of your time if you're pacing yourself on these. There's that. And now we're going to find the second derivative. Please don't do the product rule on this. Not worth your time. So 10, and then the derivative of that. So 6t minus 24. And we'll set that equal to 0. That's what we do, because that tells me points of inflection, which is where the derivative of the derivative changes signs, which is what I'm looking for, technically, so I can determine where the second derivative is negative. This does have to do with concavity. They never said concavity, but it's concavity. So 10 equals 0. No, it doesn't. 6t minus 24 equals 0. And this can happen in your head. I think that's kind of implied. So t equals 4. So let's do the number line thing. And I say the number line thing. I really mean sign analysis. Technically, that's what it's called. We are analyzing signs. And we will plug numbers into the second derivative. This should be pretty easy. If I plugged in a 2, because it's in that interval. Plug a 2 into the second derivative, I would have 6 times 2, so 12 minus 24, that's negative. So my second derivative is negative. Don't assume this one is positive. Just off the top of your head, it is, and actually you know it for several reasons, because you could plug it in and test it. You also know that this is a line, and this line has a positive slope, so it's tilting upward. So if this part is negative, then the rest of it must be above the x-axis. Just saying. But if we plugged in a 6, for example, we'd have 6 times 6, 36 minus 24, so that one is positive. But what I'm saying is, don't just always assume that if one interval is negative, the next one's positive. They don't always alternate. Just, you know that, I know that, just making sure you know that. So I want to know where the rate of change of the number of fish is decreasing. I'm looking for where the second derivative is negative, and I'm going to write that in words. So here goes. And I'm going to write it the way they worded it. The rate of change of the number of fish, I'm going to get really specific here, in the bay. If you leave that part out, that's not a huge deal. They're not going to be like, points off, you didn't tell us where the fish are. Unless, and this actually, let me go here for a second. If they would have had two functions and one of them's in a bay and the other one's in an aquarium, you would need to clarify what you're talking about. You have to make sure things are within the proper context, particularly if there's more than one context. The rate of change of the number of fish in the bay is decreasing. Okay, for what t-value, or t-values, it's values, plural, and it's all the t-values from 0 to 4. So for the values from 0 to 4, I have never seen grading be so specific that they would count off for equal or not equal here. Technically, the answer key has equals there, not a huge deal. Technically, I mean, we can make arguments that at 4, then the sign is neither positive nor negative, because that it's a 0, technically, but not a huge deal. Okay, part D. Part D is where things get a little wacky. For 0 to 8, the number of pelicans, we have another species, flying near the bay is modeled by the differentiable function p. Okay, all right, p, I don't see a p here anyway. Don't worry about it, they're about to tell us. P is a function of the number of fish in the bay. All right, when I first read it, I kind of paused there and I thought, they don't tell me p, but I know that whatever the number of pelicans is, it depends on the number of fish, and I do have a function for the number of fish. Based on the models, this model and the thing they just told me, write an expression for the rate of change of the number of pelicans. They need the derivative of pelicans flying near the bay at time t equals c. Okay, let's stop right there and think about what just happened. They told us that there's another function that is a function of the number of fish in the bay. So the number of pelicans that are flying around is going to be P of F of T, if you want to. They are talking about a specific time, C, so we're going to do that. Okay, if you put a T there, not a big deal. Now, in a minute, it'll be a big deal, but not a big deal. This, let's kind of put this in a sentence, or at least explain what this is. This represents the number of pelicans that are feasting upon the fish, that's implied. Number of pelicans near the bay at some specific time C. Now, okay, we're probably so concrete in our thinking sometimes that we're like, well, I have no idea what this even means. If I plugged in a number for C, I can find out how many fish, but I still don't know how many pelicans. You don't have to know. We don't have to know the exact number of pelicans. We can predict the number of fish, but we can't predict the number of pelicans, and that's okay. It is that abstract. Okay, but they did say, based on the models, write an expression for the rate of change. I need the derivative. I need the derivative of this composite function. That's the chain rule, my friends. So let's do it. The derivative of this, wrong letter, would be P prime of F of C times F prime of C. And this is going to be the rate of change of the number of pelicans. And I will go ahead and continue with that. So we actually know enough to do a little bit more specifically with that. If you stop here, I don't think you're going to get enough points, because you do know some stuff. You know what f is, you know what f prime is. So let's go ahead and do that. So p prime, don't know it, but we can do some stuff with the rest of it. So 10 times, we're going back to the original function here, 10 times t cubed minus 12t squared. Oh, I just made a mistake. I hope you caught it. We're not dealing with t, we're dealing with c. All right, because we're dealing with a specific time, c, whatever c is. C is our variable, sorry, t is our variable that represents time. C, in this context, represents a specific time. Okay, so this, so far, has taken care of p prime of f of c. And now we need to multiply by the derivative of that, which we, derivative of f, which we already found to be 10 times 3t squared. This is the unfactored form. 24t and 45. Okay, and I did it again. Oops. That should be a C. Here we go. And let's put it in context. Let's kind of answer the question within the context of what they asked. They said, write an expression for the rate of change. We've done that, but I want to say that's what this is. So this represents the rate of change of the number of pelicans at time t equals c. And that is all they were looking for on this one. This one was just worth 1 point.